The capsule re-enters the Earth's atmosphere and, as planned, heads toward the Utah desert where Cliff Fleming is waiting to catch it.
I felt like I was just a center fielder out in a baseball field waiting for the pop fly to come in, and everything was right on time.
Right on time, back in the control room, the capsule comes into view. But something's not right.
It's not supposed to tumble. We knew that something was wrong.
The parafoil is supposed to slow the capsule down, but it hasn't opened. The capsule tumbles out of control, and there's no way that Cliff Fleming can possibly catch it. The capsule hits the ground at over 193 miles an hour. It splits open, and the priceless wafers shatter into thousands of pieces. For the members of the Genesis team, it's potentially a disaster.
Shock, and there was silence.
My whole crew was quiet, and we're disappointed.
And back at NASA, they have a mammoth task ahead to salvage useful results from the mission. Recovering the precious solar samples from the broken gold and sapphire wafers is crucial. The major problem they face is removing the contaminating dirt from the impact, but they hope that the actual samples are still safely embedded deep within the wafers. They also have to ensure that they don't contaminate the samples further. By measuring how much dirt and top layers to remove, the scientists hope to rescue the pure solar samples beneath. These samples are made up of atoms and ions, which are atoms stripped of many of their electrons. They're minute, and the whole sample weighs no more than a few grains of salt.
They're so tiny you can't even see them, but we collected billions of these atoms and ions to analyze.
Most of the sun is made up of hydrogen, but scientists also expect to find silicon, oxygen, carbon, nitrogen, magnesium, and iron among the billions of atoms they've collected. All the elements are made up of a blend of atoms called isotopes. Scientists already know that some elements blended differently in our solar system. Only the sun contains the original blend from the molecular cloud from which every other blend came.
It's an exciting opportunity to view back in time to the very beginning, to the birth of our solar system, and try to understand where we came from.
The team has already successfully extracted the first atoms, but it will take time before they can answer all these questions. What they already know is that planet Earth is uniquely located to benefit from the sun's light and heat, and that is vital for life. We're in the temperate or Goldilocks zone of the solar system. Not too hot like Mercury and Venus, and not too cold like Mars. Instead, it's just right for life to flourish. It's 10 a.m. on our sundial, 4 billion years after the sun was born. Animals are just appearing. 35 minutes later, humans walk on Earth, our bodies created out of carbon, originally from inside a star. And today, we rely on the sun for our very survival. Its energy fuels trees and plants, which are essential for the food chain we all depend upon. And by evaporating water from the oceans to form clouds, the sun supplies us with rain to nourish our crops and fresh water to drink. This energy is created more than 93 million miles away at the heart of the sun's nuclear engine. At temperatures in excess of 27 million degrees Fahrenheit, 4 hydrogen nuclei fuse together to create a single helium nucleus. But the helium is slightly lighter than the 4 hydrogen nuclei, and it's that missing material which is converted under Einstein's famous formula, E equals mc squared, to pure glowing energy. It's given off as tiny particles of light, called photons. Every sunbeam is full of them. Every second, almost 600 million tons of hydrogen are converted into helium. That's more energy in 1 second than 6 billion nuclear power plants would produce in a year. But how does the energy reach us? The incredible journey that photons make to deliver energy to Earth is something David Bodanis, a solar expert, knows all about.
Those photons of light that come down and give you a tan after a while were created over 1 million years ago, and some were starting their journey when the dinosaurs were still around.
They battle their way through the biggest obstacle course in the solar system, starting in the sun's dense core. Here, photons zoom around at the speed of light, bumping into electrons. As they collide, photons pass on energy or momentum, just as one ball does to another on this executive toy.
They pack this terrific punch. It's just like a sequence of balls suspended on wires. If you take one back and whack it into them, the momentum pushes all the way through and makes the one on the far side fly out.
The next obstacle for the survivors is the radiative zone. Here, photons are bounced around by particles of hot hydrogen gas called plasma. They start changing direction in random ways, a bit like balls in a pinball machine, zigzagging around for years and years and years.
The photons in the sun have a journey as hard as these pinballs that spends 1 million years in the radiative zone, and they're hitting against each other all the time, bapping sideways, going backwards, occasionally going forward. For some of them, it's been the entire length of time since the sun was formed, and they still haven't made it out.
Only the lucky ones make it out to reach the convection layer, where they get a bit of a rest. In just 3 months, they're absorbed in seething rivers of hot gas and carried by their currents to the sun's surface, the photosphere. Here, the hot atoms enter the sprint section of the course. They cool and release their energy as photons once more. The photons stream into space, and traveling at the speed of light, they complete the 93 million mile journey to Earth in just 8 minutes. Finally, they arrive. Photons have been providing heat and light since the sun started glowing. By 10 a.m., the conditions they helped create gave us animal life on Earth. But where are we today on the sundial? Exactly how old is the sun? Scientists know its age because of one remarkable fact. The sun sings. It doesn't really play a tune, but scientists have discovered that massive pressure changes deep within the sun cause vibrations that resonate through to the surface and bounce around inside the sun like sound waves or seismic waves on Earth. This is the sound of the sun singing. To allow us to hear the sun's voice, scientists speed up the frequency of the sun's oscillating pressure waves 42,000 times and compress 40 days of vibrations into just a few seconds. Work on calculating the sun's age from its singing was carried out at Big Bear Observatory in California by astrophysicist Phil Goody. We know that the sun's temperature and pressure change more and more over time. Phil Goody and his team have worked out that these changes would cause the sun to sing a different song.
This is much like the case of a drum. I put my fingers on and increase the pressure, I get a higher frequency, a higher pitch. And when I take my fingers off, I hear a lower pitch. It's as though the drum, when it ages, it gets softer.
Just like the drum, as the sun ages, changes in its density, pressure, and temperature cause the sun to sing at different pitches. But unlike the drum, which loses pressure as it gets older, the sun's pressure increases, making the pitch higher. Scientists calculated at what pitch they would expect the sun to sing at each stage of its life. Finally, they matched today's song to those calculations to find out its current age.
We've been able to precisely determine the age of the sun to be 4.6 billion years old. So that's kind of a surprise.
Their discovery makes the sun millions of years older than they had previously thought. On our sundial, in which 6 a.m. marks the birth of the sun and 6 p.m. its death,